Well, hello everybody again. Welcome to our discussion of section 5.5, which is going to be about the inverse trigonometric functions and their graphs. So before we begin our discussion of this, I really want to do a quick recap of what we did in sections 5.3 and 5.4 with respect to the graphs of transformation of graphs of sine, cosine, tangent, cotangent, and secant and cosecant. Remember those? So let's do a quick recap of that material before we continue with this subject. So this is just a recap of sections 5.3 and 5.4 because I think it was very important that we really got everything down about this topic before moving forward. So when talking about transformations of sine functions, so recall that for the sine function we had a sine of k times x minus b, and let's do an f of x here. So you recall this for the sine function, this was the general transformation formula, and the absolute value of A was the amplitude. That's how much vertically the graph of the sine function is going to fluctuate. It could go from 1 to -1, 2 to -2, 3 to -3, and so on. K, so that number in front was k, and if x had a coefficient, we would have to factor it out. Remember that, in order for x to have a coefficient of 1 inside the parentheses. And we needed this k because the 2 pi over k was the period, how we could calculate the period of that particular sine function, and that would be the period would be the duration or the interval, x interval, over which the sine function goes through one full cycle. Okay, so that was the period. And b, of course, was the phase shift. And recall that once a sine function is transformed or moved in some way, we can calculate within which interval the function has moved by using this formula. So we could say that b, bracket b, comma, b plus the period, which is 2 pi over k. Okay, so this is the interval over which one full cycle takes place. Okay, so that was about the transformation of a sine function. So let's do a quick review of the transformation of a cosine function. So this is the formula for that. Once again, the same things. The absolute value of A is the amplitude. That's the distance along the y-axis vertically where this function is going to fluctuate. Again, once again, the period for the cosine function would be 2 pi over k. So that's once again true about the cosine function. The b, once again, is the phase shift. Because if there is no phase shift, the wave is going to start at x equals 0, right? So the phase shift is telling us, this b is telling us which way, whether horizontally, whether to the left or to the right, has the beginning of the sine function or cosine function has moved. So if there's no phase shift, then the function is going to start at x equals 0. But when there is phase shift, it's going to start at this, and it's going to trace over an interval which has this size. So b, comma, b plus 2 pi over k, right? That's the interval. Once again, the interval over which one full cycle takes place. So let's take a look at the transformation function for tangent and cotangent. So recall that for that we had f of x equals a times tangent of x minus b. And I should remember to add the k there. Let me put the k here, right? That's transformation of tangent function. Once again, absolute value of a is the amplitude. In this case, it would be a stretch. If this value was, say, 5, then the graph of the tangent function is more stretched along the vertical axis. And so k, or how, okay, so the period of the tangent function is pi over k, not 2 pi over k. Pi over k is the period. And this is the distance over which the function goes through one full cycle. So that is the period. And the next one, what b of course is the phase shift. And once again, the distance would be, for one full cycle, would be b comma b plus pi over k, which is the period length, right? So instead of the horizontal speaking, the function tangent, instead of starting at 0, it starts at b, and it goes to b plus pi over k, which is the period. Like that. And let's do the transformation function for the cotangent function. And that was f of x equals a cotangent of k times x minus b. The absolute value of a is the amplitude or the vertical stretch of this function, cotangent function, Period, once again, just like the tangent function, the period is going to be pi over k. And B is going to be the phase shift, that B. And of course, the interval B comma B plus pi over k is going to be the interval over which one full cycle takes place. Okay, let's do the secant and cosecant. Well, I'll just do it at the bottom here, so I'll split this bottom to 2 halves, and I'll do the f of x equals a secant k times x minus b, the same thing. So here, once again, the period is going to be, so everything else is the same, the phase shift and b and amplitude will be the same, except the period. The period is going to be, again, 2 pi over k, not pi over k. So only the tangent and cotangent have periods pi over k. And let me put the cosecant here, function here. Like that. And let me just say that I'm just going to put the period because everything else is the same as with the other 4 trigonometric functions. So 2 pi over k is the period here, and also 2 pi over k is the period here. All of this, of course, is important when we graph these functions. Okay, so this was just a quick recap of sections 5.3 and 5.4. Now, with respect to the section 5.5, or inverse trigonometric functions, we're going to look at the inverse of these 6 trigonometric functions that we've seen so far. So now, we talked about inverse of functions in pre-calculus 1, remember, in Math 126? Now, let's remember some of the things about that content area from pre-calculus 1. So we learned that, recall from Math 126 or pre-calculus 1, that a function has an inverse only if it's a one-to-one function. Okay, so let me, only one-to-one functions have an inverse. Okay, now, as you know, every single trigonometric function that we have is not one-to-one, right? Because it's periodic. The graphs are going up and down. And before I talk in more detail, let's remember one more thing from Math 126, the horizontal line test. Remember that? So a function has an inverse only if a horizontal line intersects its graph at one point. So if this is true, then the function we're dealing with has an inverse. It has to be 1 to 1. And for example, here is an example of a function that does have an inverse. So suppose I have a straight line that is going like this. So does this function have an inverse? Let's call it f of x, some linear function, right? The answer is yes, because if you draw a horizontal line anywhere here, it'll intersect this line at one point only. Then in Math 126, we talked about functions like this. The quadratic function, remember that? The basic quadratic function, f of x equals x squared. Does this have an inverse? Well, using the horizontal line test, no. It has no inverse, right? So this one, function has an inverse, and function it does not have inverse. So I don't know if you remember or not, but what we did in cases like this, we limited the domain of this function to a part where it can be intersected with a horizontal line only once. So in this situation, it does not have an inverse, right? But what if we made a change? If we restricted the domain, let's say to x greater than, but if x is greater than or equal to 0, right? So we're restricting the domain. We're saying only do this piece for which the x values are either greater than or equal to 0. So only this piece of that function. So this is still f of x equals x squared, right? But this time we've restricted the domain. So does this function, this function with restricted domain, have an inverse? And the answer is yes, and it passes the horizontal line test, right? Any horizontal line will cut this piece of the graph at one point. So it does have an inverse. Okay. Now, just remember this discussion from Math 126, because it's going to be infinitely important in this discussion of the inverse of trigonometric functions. Okay, so we're going to now talk about the trigonometric function. So we need to, by the same token, we need to restrict the domain of trigonometric functions. Otherwise, none of them will pass the horizontal line test. You remember all the graphs of the sine function, cosine function, tangent, cotangent, and secant and cosecant? None of them will pass the horizontal line test. So we need to, for each one of those trigonometric functions, we need to restrict the domain. So the question is, to what we need to restrict the domain? To what interval? So let's take a look at that. Well, first of all, I'm going to say note trigonometric functions are not one-to-one unless we restrict their domain, which is what we did here back in Math 126. So we're going to have to do that here. Okay? Because restricting the domain to a certain distance, we're going to create a one-to-one function where the horizontal line will intersect the graph at only one point. So let's look at that. So for the sine function, suppose we want to find the domain for the sine function such that we could find the inverse of it, right? So let's see how that is done. So we have y and x, and the sine function, if you recall, it does like this, right? It does something like this, and then comes like that, and on this side it does like that, and it does like that. Right. So this is the sine function, and I'm going to say y equals sine of x. Okay, for sure, this will fail the horizontal line test, right? For sure. So where can we restrict the domain? Well, if you look at this high point and this low point, right? So if we restrict the domain to pi over 2, at which sine of pi over 2, remember what that was? Do you all remember? Remember from this table of special trigonometric values? The sine of 90 degrees, or pi over 2, was how much? 1. Right? Sine of 90 degrees is 1. So at this point, at this pi over 2, the sine function is equal to 1. And at sine of negative pi over 2, it is equal to negative 1. Right? So if we restrict the domain to that distance, from negative pi over 2 to pi over 2, then a horizontal line will be able to intersect this graph at only one point. And we will have an inverse for the sine function if we restrict the domain of it to negative pi over 2 to pi over 2. So let me write down underneath it that the domain of y equals sine of x must be restricted to between negative pi over 2 and pi over 2. Okay, that's for the sine function. In other words, it'll have to be just this piece. That's it. So we're going to do that. We're going to restrict the domain of the sine function to minus pi over 2 to pi over 2, so the horizontal line crosses it only at one point, and therefore we can find the inverse sign for it. So when we find the inverse of the sine function, the inverse sine function has a slightly different notation. So the inverse will be do I want to talk about it now? Let's talk about it later, because I don't want to talk about the notation yet, because first I want to talk about the original graphs of each of these functions. So we'll get to it. I'll just wait and talk about that later. So let's talk about the cosine function. So please remember that the cosine function, it starts from high point here, comes down like this, does this, curves back up again, goes up again like that, and on this side it comes back down, goes up again, and does that. Right? That's roughly what a cosine function looks like. So y equals cosine of x. Okay, so for sure you can see that this function as it is, it will fail the horizontal line test and it will not have an inverse. So we definitely should limit the domain for it if we want to have an inverse. Well, the question is where we should limit the domain to. Well, let's see. This is 0, this is pi over 2, because cosine of pi over 2 is 0, which is that point. And then at this point, cosine of 0, if x is 0, cosine of x is equal to 1. And at this point, which is pi, that point is pi, and pi along the x-axis. So if x is pi, then the cosine of pi is -1. So if we limit the domain of the cosine function to 0 to pi, like that, for sure the function, that piece, will have an inverse, because a horizontal line will intersect that thick black line at only one point. So if we want the cosine function to have an inverse, we must restrict its domain to 0 to pi. Okay. All right. So let's look at the tangent function. So the tangent function looks like this. You know that, first of all, recall, as I asked you, to please connect these functions to other trigonometric functions. So tangent of x is equal to sine of x over cosine of x, right? Remember that? Okay. So because of this relationship between tangent and this sine over cosine, so whenever cosine of x is 0, right, we're going to have a vertical asymptote. Remember that? So where is cosine of x 0? At pi over 2, negative pi over 2, 3 pi over 2, and so on. So let me draw the asymptote. So it'll be here somewhere. And on this side, it'll be like that. So I'm going to draw just one, because you've seen that there's going to be infinitely many, right? But I'm going to draw one because that's all we need. So this would be x equals pi over 2 and x equals negative pi over 2. These are the asymptotes. So the tangent function, let's see. I believe it's going this way. So let's, for 1 second, I'm going to switch to this computer. So the Desmos calculator, so we're going to have y equals tangent of x. Yes. So let's get back to the dock camera. So we're going to have this line like that, right? Just one of those many that you saw on the computer. So that's all we need, because if you draw more, once again, the horizontal line will intersect the other ones as well as this one, and it will fail the horizontal line test. The tangent function will fail the horizontal line test. So just this one, we need to restrict our domain to just minus pi over 2 to pi over 2, and we'll be fine. Remembering that x cannot be negative pi over 2 or pi over 2, or we'll have an undefined tangent function. So here we'll say the domain of y equals tangent of x must be restricted to x being between, not equal to, let me make sure that that is like that, x greater than, not equal to, minus pi over 2, x less than pi over 2. So we can't go beyond this limit, otherwise the tangent function will fail the horizontal line test. Okay. Then the next one, let's look at the cotangent function. Let's look at that. So the cotangent function, I think I can fit it in this corner. Y equals cotangent of x. What connection does this function have with the tangent function? Well, it's the reciprocal. Cotangent function is the reciprocal of the tangent function, and vice versa, right? So if I flip these, if I write cosine of x over sine of x, I'll be able to get the formula for cotangent function. But now I have a fraction, and sine of x cannot be equal to 0. But where is sine of x equals 0? Because I need that information in order to know where are my vertical asymptotes. Well, the sine function is 0 at x equals 0. It's 0 at x equals pi, 2 pi, 3 pi, and so on and so forth, right? So so here is one of the asymptotes. So one of the vertical asymptotes is the y-axis. So I'm just going to put a dashed line right next to it. And then pi, right? Let's say that is pi. Like that. So this is x equals 0. This one is x equals pi. Well, let's draw the cotangent, which is, notice how this is going. This is the reciprocal of that. So the graph is going to go the opposite, like that. And you know where that point is, right? That point at which the cotangent function is equal to 0, it's going to have to be pi over 2. I mean, not only it's halfway between 0 and pi, but because when x is equal to pi over 2, cosine of pi over 2 is equal to 0, and 0 divided by anything is 0. So we know that's pi over 2. Okay, so we need to restrict the domain for the cotangent function to x greater than 0 and less than pi. We can't go further, because if you draw one more of these lines, a horizontal line can be drawn such that it'll intersect that function at 2 points. Remember, this is not the full period, right? This is not the full. In order to draw the full period, we need to draw a piece of the other side here after pi. But we can't. If we do that, we're not going to be able to find the inverse of this. So domain, in order for us to be able to find the inverse of the cotangent function, the domain has to be restricted to x greater than 0 and less than pi. Let's write that down. Like that. Okay, so we have two more functions to look at, right, to see where their domains must be restricted. And that is the cosecant function and the secant function, or secant and cosecant, makes no difference. So let's draw the secant function first. I hope you see why for each of these tangent, cotangent, cosecant, secant, you should remember to which trigonometric functions they are connected, because that's how you can decide where the vertical asymptotes are and how to draw their graphs. So it's very, very integrated subject. So like that. Okay. So if we say y equals secant of x, remember what other trigonometric function secant of x is connected to? Do you remember that? We know that secant of x is the reciprocal of cosine of x function. Okay, so if it's the inverse, or not inverse, but reciprocal of the cosine of x function, then wherever the cosine of x is 0, it's going to be undefined, right? So where is cosine of x is undefined? Remember from there? I mean, where is cosine of x equals to 0? If I bring back the table of special values, the cosine function is 0 at 90 degrees, pi over 2, right? So at pi over 2, we're going to have an asymptote. Let me draw that. Like that. And this would be x equals pi over 2. Also, we will have an asymptote at negative pi over 2. Okay. So the cosine function, first of all, would be 0 at that point, right? The cosine function itself. So if we roughly, let me draw that in a rough sketch. I'm going to use my black ink to draw the cosine of x function. So it's going to act like this. Come back up and do this. On this side, it's going to do like that. And it's going to do that, right? That's the cosine of x function. That's not secant. This is cosine of x function. Now the secant, remember, it would go like here. It would go in between these two asymptotes, touching barely the top of the cosine and coming back up like that. But I can't do that. If I draw the full secant graph here, it will fail the horizontal line test. So what I'm going to do, I'm going to draw this piece of it. Let's see. So I'm going to draw this piece like that. Right? I'm not going to draw the other arm because it's going to fail the horizontal line test. So that's one piece of it, but I need the other piece. The other piece, I can't go on this side. I cannot complete this side. So let me do it on this side. On this side, the second piece would be like this, right? Coming from negative infinity and curving like that. But again, I cannot complete the full curve for the secant function because if I do, it'll fail the horizontal line test. So I'm going to do a partial drawing of that. So I'm going to do that like that. So I didn't draw the other piece of this arm that will curve back. So if we restrict the domain like this, from 0 to pi over 2, and, well, let's, I need to draw this, so it needs to be restricted here. At peak, it'll be pi, so this is pi over 2, and this is pi, right? That's where this function, secant of x will be negative 1. So at that point, it'll be negative 1. At this pi point, it'll be 1. So if we restrict the domain to 0 to pi over 2, we can't go that way, right? Because if we go, I'm going to have to complete this, and we can't do that. So we have to stay this way. From 0 to pi over 2, it's going to be one interval, and then from pi over 2 to pi, it's going to be the other piece. So let me write that down. Domain of y equals secant of x must be restricted to these two. From 0 to pi over 2, So it will be, let's see, so it can it attain 0? Yes, it can attain 0. So x greater than or equal to 0 and less than pi over 2. It cannot attain pi over 2, so it's less than pi over 2. And also x should be greater than pi over 2. Pi over 2, like that. And less than or equal to pi. And this domain represents these two pieces, the domain for these two pieces. Okay, and then the horizontal line will not be able to cross the graph of the secant function at more than one point that way, once we restrict the domain to that. Okay, let's do the same thing for the cosecant function. All right, so y equals cosecant of x. Do you remember which other trigonometric function this is connected to? Think about it. Do you remember? Cosine of x, cosecant of x is related to the reciprocal of the sine function. That's important. Why? Because this will tell us whenever the sine of x function is equal to 0, which would be at x equals to 0, x equals to pi, x equals to 2 pi, and so on and so forth, the cosecant function has a vertical asymptote because it's undefined at those x values. So let's draw the vertical asymptotes first. So 0 would be 1. That would be x equals to 0, which is the vertical axis y. So I'm going to put a dashed line right next to that y-axis to indicate that. So x equals 0 is one of the asymptotes, and the other one is pi. That's another asymptote. So, and the other one will be minus pi, right? So let's draw that on this side. At these values of x, the cosecant function is undefined because the denominator is going to be 0. Okay, I'm just going to roughly draw the sine curve before I draw the cosecant curve, right? So the sine curve would look like that. It would be like this, curve back down, go through this, and then comes back up again like that. On this side, it'll come up, come down like this, and go back and do that. Okay, that'll be the sine curve, or roughly the sine curve, right? I couldn't draw it perfectly. But now, the cosecant, remember, it would be, the way we would draw it, it would come down here, touch the top of the sine curve, curve back up again, like a bowl shape, right? That would be the cosecant function. And it would do the same thing on each side of this. But remember, we can't curve that line, or otherwise it's going to come back up because the horizontal, it would fail the horizontal line test. So what can we do? Well, we can draw one here. So one of the pieces would be this one, right? That's one piece. So far, the horizontal line will intersect this red arm at only one point, right? So, and that's y value equals 1. And then I can curve back up, because if I do, it will fail the horizontal line test. So where else should I go to draw the other arm? Can I go this side? It looks like it. Yeah. It looks like I can. Can I go? No, I can't go this side. I can't continue this side because it will fail the horizontal line test. So I'll have to come this way. So the other piece would be right here, from here and then here, like that. And this would be -1 along the y-axis, right? So here are the two pieces, that one and that one. Now that we've figured out where the cosecant function should be limited graphically, let's write down the restriction for this domain, because this spot right here, it should be pi over 2, which means this spot should be minus pi over 2. Okay, so the domain for the cosecant function, domain of y equals cosecant of x must be restricted to these two regions. So I'll try to fit it in here. Sorry for cramping all this on one page. Because I'm going to post all of this, the notes as well on Canvas, I wanted you to have all of this on one page rather than multiple pages. It's easier to look up and down the page and make a connection between all these different graphs, because there is a connection. Okay, so for this piece, x should be between equal to or greater than negative pi over 2, like that, and 0. It cannot be equal to 0, right? So less than 0. And x should be, for this piece, so what we wrote down is for this piece. For this piece, x should be between, it should be greater than 0, less than or equal to pi over 2. So the domain of the cosecant function should be restricted to these two regions, such that it will have an inverse. Okay, so now that we've talked about that, we can now talk about the properties of the inverse functions, because everything we did on this page from top to bottom was figure out how we should restrict the domain for each of these 6 trigonometric functions so that we can write down an inverse for it. So the domains that we figured out here are very, very important for each of these functions. As a matter of fact, let me go back and box all of these. So that's for the sine function. This was for the cosine function. These are all the restricted domains, right? This was for the tangent function, for the cotangent function, and then for the secant function, and of course for the cosecant function. Okay. So let's take them one at a time, now that we've figured out the domains. This is the inverse of sine function. And just so that when you read different books, you become familiar with these. These are AKA arcsine or defined by arcsen. Arcsen. So these are what you might see in books. Arcsine means the inverse of the sine function, or arcsen means the inverse of the sine function. So I'm going to, for this, I'm going to draw a little graph just to remind ourselves what we agreed to define, to restrict the domain to, right? So I'm not going to draw the whole thing, but just a reminder. We decided to restrict this domain to like that. If you go back to those graphs that we went over, you're going to see this. And so this will be, and this would be the 1, -1, and here would be pi over 2, and this would be negative pi over 2, right? So we decided to restrict, I'll start here, restrict, I'm going to put a bullet here, restrict the domain to this bracket negative pi over 2 comma pi over 2 bracket. So over here, if we restrict the domain to this, then notice the notation. F of x equals sine of x has domain minus pi over 2 comma pi over 2 and range can you see what the range is from the graph? What would the range be? The range is -1 comma 1, right? It's clear from the graph. So from Math 126, what do we remember from the relationship between the domain and range of the original function and the domain and range of the inverse function? Do you remember what relationship it is? Well, the relationship is as follows. The domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. So we have to switch these. So therefore, and here's the notation for the inverse function. It is f, if the original function is f of x, then this will be f minus 1 of x equals sine minus 1. So this is not a power. This is not a power. It's just a notation. It's just the way we represent the inverse of a certain function. So if you tell me this is the function you have, then I'll write the inverse with this notation. That's all. So this one has domain What should the domain of the inverse function be, looking at this? It should be this, right? Because the role of the domain and range are swapped when we are writing the domain and range for the inverse function. So the domain should be -1, 1, right? And range, the old domain will become, the domain of the original function becomes the range of the inverse function. So it will be bracket -π/2, π/2. Okay. Now suppose that y represents an angle and x is any real number. Okay, give this presentation, then if we have sine of y equals x, then the inverse sine of x equals y. This is very, very important. It's very, very important because it tells you why. What? It tells you that the result of any inverse function, any inverse trigonometric function, is always an angle. I want to box this too because this is what I'm trying to emphasize. Let me repeat this. The inverse trigonometric function, any trigonometric function, the result of that is an angle. So the other side, whatever it is, it's an angle. And x is any real number, and y is an angle. Okay. Now the properties. So by the way, this was what I drew here. This is y equals sine of x. I have not yet drawn the graph of the inverse function. So let me do that. Now that we know that, I should have probably done it here. As a matter of fact, I can. So let me draw it here next to that. So notice that the domain, that is along the x-axis, right? It's going from -1 to 1. -1 and 1. How about the range? It's from -π/2 to π/2. So π/2, you know that's 3.14/2, right? So it's a little bit over 1. So that increment should be larger than this. So let me make it here. So that's π/2, and way up, way down here, and that's -π/2. I'm going by that. Okay, so if we put a point here and a point here, then the graph of, maybe I should use a blue ink like this. I'll use my thicker marker. So it'll be like that. So that's the graph of the inverse sine function. So this would be f inverse of x equals sine inverse of x. So you have This is the graph of sine of x, and this is the graph of inverse sine of x. So notice the role, the domain here was minus pi over 2, 2 pi over 2. This is negative 1 to 1. The range was 1 to negative 1 to 1. Here the range is negative pi over 2 to pi over 2. So the role of the domain and range are swapped. This is true for any inverse set of inverse functions. We learned this in Math 126. Okay, so let's solve some examples of working with the inverse sine function. Okay, so we have example A. We have sine of minus 1. So inverse sine of 1 over 2, we ask what that is equal to. Well, remember from the, let's see. I want to make sure that I have these things in order. Okay, remember what I boxed here. The inverse of any trigonometric function is going to result in an angle. So here, what this question is asking, the sine of what angle is equal to 1/2? That's what it's asking. Because the inverse of any trigonometric function results in an angle. So this one is asking for an angle. What angle has a sine of 1/2? Well, that's why I asked you to please memorize the table of special values for trigonometric functions, because the sine of 30 degrees or pi over 6 is 1/2. Okay, so that's the angle we're looking for, pi over 6 or 30 degrees. So the result here is pi over 6. Okay, let's do another example. B, we want to know the inverse sine of minus 1/2, and we're asking about that. So here they're asking the sine, what angle has a sine of negative 1/2? Well, certainly this is not in the first quadrant, right? Let's bring this back. We know it should be pi over 6, but in which it can't be in first quadrant. So let's bring this back. This is it's too big for the screen, but I can just show the part that is relevant to our discussion. So this would it be in the second quadrant? No, because the angle is negative, the result is negative. Here the sign would be positive. In the first and the second quadrant, the sign would be positive. In the third and the fourth quadrant, that would be negative. So this would be minus pi over 6, because that would be in the fourth quadrant, right here. I think I should explain this. Remember, for the inverse sine function, what was the domain? Let me bring this down. For the inverse sine function, the range, the angle range, not the domain, but the angular range was minus pi over 2 to pi over 2, right, for the sine function. So here, there are only the third quadrant and the fourth quadrant where the signs are negative. In the other two quadrants, quadrants 1 and 2, the signs are positive. So we're not in either one of these quadrants. We're here, either in the third quadrant or the fourth quadrant, because the signs are negative, which is our case, right? Which is in our case. So now, we're either here in the third quadrant or in the fourth quadrant. But which one? Well, we have to be in the fourth quadrant, because if you're in this quadrant, then the theta, it would be, the reference angle would not be pi over 6. So here, but if we're here, negative pi over 6, we can be in the fourth quadrant and the sine value is negative. Because we have, remember, we have to be in this range. We can write down an angle that is outside of this range for the inverse. Remember that? Because we restricted the domain to negative pi over 2 to pi over 2. So the range will be restricted as well. It's not just the domain. Once you restrict the domain, you're going to restrict the range as well. So because we restricted the domain to pi over 2 to minus pi over 2, so only in fourth quadrant we could be, so it's x equals minus, so the result of this is minus pi over 6 in the fourth quadrant. Okay, so part C, the inverse sine of 3/2. So this is an angle whose result should be 1.5 or 3.2. Look at this. I mean, the x values cannot be out of this range. And this is 3/2, right? We restricted the domain. This is the domain, this is the range. So the domain, 3 over 2, is outside of this domain for this inverse sine function. Okay, so it's undefined. So this is not defined. So we cannot have that for the inverse sine function. Oh, I just remembered that this question that I'm about to ask, let me write it down. Before we answer this, we need to mention, let me draw something here, and because I don't want it to get mixed with these other ones. I should have talked about this, but it skipped my attention. These are called cancellation properties. Or cancellation property. And what it says is this, that inverse sine of some value is equal to that value. And this is true for any x between -1 and 1. Remember, that's our domain, right? For the inverse sine function, that's our domain. So this is true for that. Not true for outside of this domain. So cancellation property is if you take the sine of the inverse sine function at some value, that'll cancel each other out and you end up with this x value. By the same token, inverse sine of the sine of some value is also equal to x. And this is for, we're talking about the range here, right? The range of so this is talking about the range of the sine function cannot be beyond 1 and negative 1 and 1, which is what we established here in this graph, negative 1, 1 for the sine function. X here is the range of the inverse sine function. And what did we say about that? It cannot exceed or be outside of negative pi over 2 comma pi over 2. So we say that here for x between negative pi over 2 and pi over 2. So these two I should have mentioned earlier, but I'm mentioning it here, and in order to make sure that it doesn't get mixed in with these examples, so I'm going to box it. This is very, very important. This is the cancellation property. I'll just box that here as well, like that. Okay, now we can answer that, right? So this is asking for an angle. That angle cannot be outside of negative pi over 2 and pi over 2. Is that true? Because these two are going to cancel each other. We get pi over 6, just like what this is saying, equals x. Yeah, it's true. So we can write down pi over 6. So that was not defined, and this is pi over 6. And this is by cancellation property. So because of this is why we have that. E, so sine, inverse sine of sine 10 pi over 3, and we're asking what is that equal to? Well, inverse sine of this, 10 pi over 3, is way outside of the domain we have for this, right? The domain for the sine function is negative 1 to 1. This domain is much, much larger than 1. Much larger. So we can't really, we don't, at this point, we need to do something before we answer this question. Right away, we can't do that because this is outside of this domain. It's much larger than 1. 10 pi over 3 is much larger than 1. So let's see if we can do something to answer this question. Well, this is equal to sine of, inverse sine of this 10 pi over 3 can be written as 9 pi over 3. Let me do it in steps. 9 pi over 3 plus pi over 3. Right? So I broke this up, 10 pi over 3 to 9 pi over 3 plus pi over 3. We can do that, right? That's 10 pi over 3. It's the same thing. And that is equal to inverse sine of 3 pi plus pi over 3. Okay, so then after this, so 3 pi over 3, what does this really mean? Let's look at this. What is that angle here? Because the sine of that needs to be calculated for here. We need to find out, in order to answer this original question, we need to figure out what is inside this parentheses. And that is sine of 3 pi plus pi over 3. So where is 3 pi? If we go one full revolution, if I start from here and go all the way around, that's 2 pi, right? I'm back here from 0 to 2, that's 2 pi, going around the circle once. Then if I go one more pi, that is 3 pi, right? So I'm going to go around and end up here. That's 3 pi, right? Plus pi over 3, which would be here. So 3 pi plus pi over 3 is going to end up in the third quadrant, where sine of x is negative. So we're going to calculate sine of x. It's going to be negative value, and it's going to be square root of 3 over 2, right? That's pi over 3. Sine of 60 degrees, or pi over 3, is square root of 3 over 2. But we are in the third quadrant. I just showed you, right? If you go 3 pi plus pi over 3, you're going to end up in the third quadrant. Okay, let me do it again because I'm not sure if you follow. Here, we decompose 10 pi over 3 to 9 pi over 3, which is 3 pi plus pi over 3. We did this to figure out where this angle is going to be, such that it should be between negative pi over 2 and pi over 2. So, after that, we end up with 9 pi over 3 is 3 pi plus pi over 3. So let's figure out that where this is, such that taking the sine of it, we know in which quadrant we are, right? So 3 pi would be going around. 2 pi would take me one full cycle around this circle. So if I go once over this entire circle, that'll be 2 pi. I'm back in where I started, 360 degrees. Then this is 3 pi. So I need to go one more half of this circle, 2 pi. So if I go from here to here, that makes it 3 pi. So plus pi over 3, which is 60 degrees, I'm going to end up in the third quadrant. That's important because the sign of the pi over 3 in the third quadrant is negative, and it's negative square root of 3 over 2, which is, we know it from the special table of values. Sine of pi over 3, or 60 degrees, is the square root of 3 over 2, but in our case it's minus square root of 3 over 2 because we're in the third quadrant. So therefore, let me write here, so that is equal to inverse sine of minus square root of 3 over 2, and that is equal to, we're in the third quadrant, so this angle has to be negative, so minus pi over 3. Right? Pi over 3. But it's negative in our case, so it is minus pi over 3. Okay, so that's that. Let's look at the inverse of cosine function. AKA, these are different names for the same thing. Arc cosine, which is defined by like that. So that's a mathematical notation for inverse cosine function. Okay, like that. So if you see that notation, that means inverse cosine function. Okay, so here, let's look back at the graph of this, where we had to, I have to pull that sheet, so we decided to restrict the domain to this piece here, from here to here, so like that. And this is y equals cosine of x. That's the graph of that. We decided to restrict this domain to 0 to pi, I believe, yes. So 0 to 2, 0 to pi. And this is 1. And from here, this is negative 1. Okay, so let's write the same things down here. So we want to restrict the domain to 0 to pi, right? So we know that f of x equals cosine of x has domain 0 pi and range of negative 1 comma 1. You can see it in the graph. Range from negative 1 to 1 and domain 0 to pi. That's when after we restrict the domain, which in turn restricts the range, right? We had to do that. We discussed that in the beginning. Okay, so now the inverse function so the inverse function of inverse cosine function has domain. What do you think the domain of this will be? We have to swap these two, right? For the inverse function, the domain and range are swapped. So now the range is the range of the cosine function is the domain of the inverse cosine function. Like that. And range, so the domain will be the range, 0 pi. So if we have cosine of y equals x, remember this y is now an angle. Okay, as a matter of fact, let me write that. So I'll write it underneath it this time because there's not much room there. If that's the case, then the inverse cosine of x equals y. Very, very important. Again, the inverse cosine function or the inverse of any trigonometric function leads to an angle. So this y, so x is any real number and y is an angle between, of course, 0 and pi. An angle in this interval in 0 comma pi. So this y is an angle. That's the important thing to remember. Okay. And also by cancellation property, in this time I didn't forget to write this down. So by cancellation property, we have a cosine of inverse cosine of x equals x, and this is the range, this x is the range of the cosine function, which we know was 1, 1 and negative 1, right? So this is x must be for x between negative 1 and 1. And this is the range of the cosine function. So inverse cosine of x, again it's equal to x, but this time this x is in the range of the inverse cosine function. And what is that? That's 0 to pi, right? Range of the inverse cosine is 0 to pi. So then x must be between 0 and pi, like that. So we drew the graph of the cosine function. Let's draw the graph of the inverse cosine function. I'm going to draw it here. You can easily see how the graph should be drawn from here. The domain should be between negative 1 and 1. Okay, that means I need to put negative 1 and 1 here. Good. And the range should be between 0 and pi. So 0 here and pi up here. Pi is 3.14. So if I drew my graph to scale, that should have been 3 times this distance. Unfortunately, I didn't put these increments in the right place. But let me try and put it up there. So let's just assume this is pi. Let's just say for the sake of this graph. But I acknowledge that this is not to scale because pi is 3.14 if we round it. And this is just 1. So realistically, this distance here should have been more than 3 times this distance. And it's not. And it's just that I'm a little bit out of space here. So I'm drawing a small graph. Okay, so, and then we have this point here, and we have this point. So our graph is going to look like this. I'm going to draw it in red ink. Okay, and right there, that should be pi over 2. Let me see. So cosine of, inverse cosine of pi over 2. So this would be halfway. So that would be pi over 2. Yes, so pi over 2. Okay. So let's do some examples like the previously. So we want to know inverse cosine of square root of 3 over 2. So that's the question they're asking us. So if you remember the special trigonometric table of special trigonometric values, so this question mark is an angle. That's what I was emphasizing up here. Remember, the inverse of any trigonometric function always leads to an angle. So this question mark is asking us to determine what angle has cosine of square root of 30. Cosine of what angle is square root of 3 over 2? That's what this question is asking. So we know that from the special trigonometric tables, we know that that would be 60 or 30 degrees. So, right, 30 degrees. Cosine of 30 degrees is square root of 3 over 2, and it's positive. and that's pi over 3, or sorry, pi over 6 is within this range. Okay, so it is within 0 to pi. So it's equal to pi over 6. Okay, so B, inverse cosine of 5 pi over 6. So this is an easy one, right? So this is an easy one because by cancellation property, this is going to equal to 5 pi over 6. So by cancellation property, which we have in here, so it's this one. So it's this property, inverse cosine of 5 pi over 6 is equal to 5 pi over 6, which is x, right? Note that we can do this because 5 pi over 6, we can do this right away because 5 pi over 6 is within this range of values, within this x values, right? If it wasn't, we'd have to break this up. We'd have to break this up like we did with 10 pi over 3, remember, for the sine function. We have to break it up. In this case, we don't have to do that, so we can just write this by cancellation property, which is that one. Okay, C. We want to find inverse cosine of pi over 3. That's the question, right? So notice 5 pi over 3 is outside of this range. It's outside of that. So we need to break this up. So let's break this up to, let's see, we have 3 pi over 3, that's just pi. So we're going to break this up to inverse cosine of 3 pi over 3 plus 2 pi over 3. We need to find the angle. That is, we need to find, let me take you back to the first lecture or first video. We need to translate this into its reference angle. That should be between 0 and pi, and then we can answer this question. So that's what we're doing. We're finding the reference angle for this. A reference angle that is between 0 and pi. Okay, so 3 pi over 3 plus 2 pi over 3 is the same thing, right? 5 pi over 3. So 3 pi over 3 is pi plus 2 pi over 3. And that 2 pi over 3 is a slightly less than pi. So it looks like we're going to be in the fourth quadrant, where the cosine value is positive, right? We're going to be in the fourth quadrant because this 2 pi over 3 is a slightly less than a pi, 4 pi, and we already have pi, so pi plus something that is a little bit less than a pi. So that pi would be all the way to here, 180 degrees, and add to this 2 pi over 3, which is a little bit less than a pi. So we end up in the fourth quadrant where the cosine value is positive. Okay, so 2 pi over 3 will take us to, let's see, so this would be So this is, let me write this down here. So 2 pi over 3, we're in the third quadrant. So what is the reference angle for that, right? 2 pi over 3 would be 2 times 180 is 360 divided by 3, so 120 degrees. So 120 degrees, that would be the reference angle, would be 60 degrees. Remember, the reference angle is the shortest distance between the x-axis and the terminal point. So if we trace that angle, this angle, pi plus 2 pi over 3, will end up here in the fourth quadrant with the reference angle being equal to 60 degrees. Let's see. Yes, so this would be inverse cosine of pi over 6. Again, this pi over 6 is the reference angle for this. So cosine of pi over 6, or cosine of 30 degrees, is square root of 3 over 2. But let's look at it. No, cosine of pi over 6. Let's see. So pi over 2 pi over 3. I should do a quick calculation, guys. So 2 pi over 3. So that would be 360, 120 degrees. And so that would be, let's see. So that would be 120 degrees, right? So 2 pi over 3. So that's 360 divided by 3. So that would be 120. And 120. So this would be, I didn't mean to actually write that. So this, I need to correct this, guys. So that 2 pi over 3. 1 second for me to get my calculator here. Okay. So 2 times 180 divided by, so that's 120. So like that. Let's see. So 120 degrees. So we want to take the cosine of that. It should be. So I'm pretty sure this is not right, but so cosine of that, cosine of 120 degrees, it would be minus 0.5. Yes. So that, but it's in the fourth quadrant, so it would be positive. So please disregard this minus because we're in the fourth quadrant, and so this will be 1. So this whole thing is 1 over 2. It's 1 over 2. So we're taking the inverse cosine of 1 over 2. We're finding the angle for which the cosine is 1 over 2. And that would be cosine of pi over 3. So this would be pi over 3, like that. Okay. All right. So let's do more examples. Suppose that was C. Let's do D. We want to find inverse cosine of 2/3. We're asking for that. So if I find this sheet, so notice that we're looking for an angle. This question mark is an angle which we're looking for, and this number 2/3 is slightly less than 1, right? So by cancellation property, so this cosine, this is the range of the cosine function, right? Range of the cosine function by cancellation property can be anything between 1 and -1. Okay, that's that. So we can just say by cancellation property is equal to 2/3, which would be x, right? So I'm not sure if in the video I'm able to explain this well enough for you so you can see what happens here. The previous example, see this one. The previous example was inverse cosine of cosine function. So in the cancellation property, the x should be in the range between 0 and pi. And for sure, the answer we found here, pi/3, is within 0 and pi. It's a valid answer. But this time, it's not. This time, in the next example, it's not inverse cosine of cosine. It's cosine of inverse cosine. Cosine of inverse cosine. So now, this x, this question mark, should be in the range between -1 and 1. And 2/3 is between 1 and -1. So we can just write that is equal to 2/3 itself. By, and let me add here, by cancellation property. Okay, let's do another example. We want to this time, notice the notation. This was cosine of inverse cosine. This one is inverse cosine of cosine of minus pi/6. And that's what we want to find out. So minus pi/6 is in the fourth quadrant, right? In the fourth quadrant, let me bring this sheet back. In the fourth quadrant, what is the cosine x value? Is it positive or negative? It must be positive, right? Okay, because let me make sure that everybody follows this. So it's positive because the terminal point for any angle in the fourth quarter or fourth quadrant has cosine of x as the x value and sine of x or theta as the y value, right? So x values, which are, in this case we have the cosine, which is the x value, equivalent to x value, right? X are cosine theta. We showed this in the first lecture or in the first video, and so all the x values in the fourth quadrant are positive, which is the cosine value. So we know the angle that the result that we're gonna end up here is gonna be as a positive result. Okay, so cosine of negative pi/6, we know that. So let me add here that because cosine of x is an even function, therefore cosine of negative pi/6 is equal to cosine of pi/6. Remember that? This is all from the previous classes, right? That cosine function is even, so that is equal to that. So let's substitute for that with this, with the with its equivalent, because cosine is an even function. So we say, so we have I'm going to rewrite this, but substitute this with cosine pi over 6. So cosine inverse of cosine of pi over 6, right? That's what we're looking for. So this is easy because this is just saying cosine of 30 degrees. What is the cosine of 30 degrees? It's square root of 3 over 2, right? We know that from the special table of values. The 30 degrees has cosine of square root of 3 over 2. So I'm just going to plug in here. So this is equal to cosine of square root of 3 over 2. Oh, sorry. Then I should remember to put the inverse there. So inverse cosine of cosine pi over 6 is equal to inverse cosine of square root of 3 over 2. So now this, so I want to write this down so it's part of your notes. The question mark is an angle such that cosine of the question mark is equal to square root of 3 over 2, right? This is why when we were doing this, I emphasized you to remember this. This is very, very important, and I even boxed it. So when you go through these notes, please make sure you pay special attention to anything that is boxed, because these are things that we use again and again and again. So we ask, what is the angle cosine of which is the square root of 3 over 2, and it's pi over 6? We could have said that by cancellation property too, right? So this is equal to pi over 6, and let me, so that by cancellation property. And for sure, that angle pi over 6 is for sure between 0 and pi, right? When we have, for the cancellation property, inverse cosine of cosine equals x when x is between 0 and pi. Inverse cosine of cosine is equal to pi over 6 in this case, which is for sure between 0 and pi. Okay, let's do one more example. So this would be f. We want to find inverse cosine of cosine of 17 pi over 6. Okay, so compare this. Inverse cosine of 17 pi over 6. This is a very large angle, many cycles. Well, it would be more than 3 full trips around the fourth circle, more than 3 times or around the circle. But we want inverse cosine of cosine, an angle between 0 and pi. So we need to break this up so we can get an angle between 0 and pi, right? That's inverse cosine of cosine. Inverse cosine of cosine by the cancellation property should be an angle between 0 and pi. Okay, so let's break this up. That's what they're asking us. And we're going to say this is equal to, let's see, so if we have 12 pi over 6, that would work, yeah. So let's do 12 pi over 6 plus pi over 6, right? We need to break this up. And so this is simply 2 pi, right? Cosine of 2 pi plus pi over 6. But we know from before that cosine has a period 2 pi. So this is equal to, so cosine, I'm going to say recall, cosine of x equal to cosine of 2 pi plus x, right? Remember that? We talked about this before. So cosine has period 2 pi. So we can replace this whole thing by its equivalent, which is 5 pi over 6. After we broke this up, this is the benefit of that. So we can reduce this angle to something between 0 and pi. So therefore, we have inverse cosine of 5 pi over 6. So 5 pi over 6 is slightly less than pi, right? So let me find my circle here. So if pi is from here to here, right? 5 pi over 6 is somewhere in the second quadrant where the, let's see, so in this quadrant, the cosine should be negative. Yeah, it is negative. So, so this is, okay, so that's that. Oh, so this is just, we're almost done, actually. So, almost done. So this is, that this angle is between 0 and pi. So by, this is inverse cosine of x should be equal to pi over 6, right? By cancellation property. I'm looking at that. Inverse cosine of cosine equals that x, in this case, in our case, is 5 pi over 6 for x between 0 and pi. So this is equal to 5 pi over 6, and we are done. Okay, so now let's move to the inverse of tangent function. I will go to a new page. The inverse So if you see this symbol, arctan, that's another way of saying inverse tangent. So you can either see this or tan or tan inverse -1 on top and in parentheses x. So these are different ways of notating inverse functions. Okay, so here Remember that from that set of graphs we did earlier, let's see, it was somewhere here. So for the tangent function, we had to restrict the domain to minus pi over 2 to pi over 2. Remember that from one of the earlier pieces we did today? Okay, so I'm just going to duplicate that graph here. So we also have it here. And we have y equals tangent of x, which is equal to sine of x divided by cosine of x. And of course, this would be between pi over 2 and negative pi over 2. And the graph was like this. Okay, so here we decided to restrict the domain to negative pi over 2 to pi over 2, right? So restrict the domain to, we can't include negative pi over 2 or pi over 2, right? Because it would make this denominator cosine of x equals 0, which we can't have. So it's going to be parentheses negative pi over 2 comma pi over 2. Then, so looking at this graph, we know that for f of x equals tangent of x has domain, do you see the domain? It's going to be the same thing, negative pi over 2 to pi over 2. And do you see the range? The range is going to be negative infinity to infinity. And range negative infinity to infinity. Now, for the inverse function, the role of the domain and range are reversed. So let's see. And so I'm going to write that here. So the inverse function, inverse tangent function, like that, has domain. Can you tell what the domain is going to be? Exactly. It's going to be the range of the original tangent function. So it's going to have the domain negative infinity to infinity and range the domain of the original function. That's going to be the range. So minus pi over 2 comma pi over 2. It seems that I don't know if that's, it looks like out of focus, so let me try to improve that. Okay, that's better. All right, so then if we have tangent of y equals x, then inverse tangent of x equals y. This is very important, right? So y, the inverse tangent, like I said earlier, the inverse of any trigonometric function produces an angle. So this y is an angle, and x is any real value, let's say. So x real value on the real number line, and y is an angle between negative, well, no, let's see. So that is, let's see. So the range, that would be the range of that. Yes, so between negative pi over 2 and pi over 2. Okay. Okay, all right, so that's that. Now, we also have cancellation properties here. And so according to the cancellation property, if we take the tangent of inverse tangent in x, that'll be equal to x. And this is in the range of, this x is in the range of tangent, right? And tangent had negative infinity to infinity. So let's say for x from negative infinity to infinity. I'm just rewriting this. The range of the tangent function, which is that, is going from negative infinity to infinity. And the inverse tangent of the tangent function is also equal to x, but this x is in the range of the inverse tangent function. And the range of the inverse tangent function is minus pi over 2 to pi over 2. So this has to be 4 x between negative pi over 2 and pi over 2. Okay. So how does the graph look for the inverse function? Well, this is going to give us a clue how the graph is going to look, right? The range is going to be between negative pi over 2 to pi over 2. That's along the y-axis. And the domain is going to be negative infinity to infinity. So we can, right from this, we can draw our graph. So let's do that. So the range is going to be minus pi over 2 to pi over 2. That's along the y-axis, right? So let's draw horizontal asymptotes there from pi over 2. So this is going to be positive pi over 2. And this is going to be negative pi over 2. Like that. So this is going to be y equals pi over 2. And here y equals minus pi over 2. I should have. So let me make that blue ink. Like that. So the domain is going to be negative infinity to infinity. So this is going to look like this. Like this and like that. Okay, so this is the graph of y equals inverse tangent of x. So that's the graph of the inverse tangent function. So let's do some examples. Well, I want to do the examples on the next page because this will really crowd this page. So let me not do that here. I'm going to go to the next page. So here we have okay. So example part A, we want to find out the value of inverse tangent of square root of 3 over 3. Okay, so we know that this value is an angle. So must be some angle between negative pi over 2 and pi over 2. Some angle in this range, minus pi over 2 to pi over 2, right? And we saw that the angle should be between negative pi over 2 and pi over 2. It cannot be beyond that. So must be some angle between negative pi over 2 and pi over 2. So which one is it? Well, according to the table of special values, if I can find it, so we ask what angle has a tangent equal to square root of 3 over 3, or tangent of what angle is equal to square root of 3 over 3. So here's the table of special values. Tangent of what angle is equal to square root of 3 over 3? 30 degrees, or pi over 6. So the answer to this is pi over 6, right? That one. B, we ask what is the inverse tangent of 0? So again, we're looking for an angle such that the tangent of that angle is equal to 0. That's what this question is asking for. Well, tangent is equal to sine over cosine. When sine is equal to 0, the tangent is equal to 0. And 0 is between negative pi over 2 and pi over 2, positive pi over 2. So this will be 0. That's the angle. And then another example. We want to find out the tangent of, or inverse tangent of negative square root of 3 over 3. So this is, remember, this angle should be between negative pi over 2 and pi over 2, like that. So in which quadrant is the tangent negative? In a quadrant where either sine or cosine is negative, right? But if we are between pi over 2 and negative pi over 2, then we should be either in quadrant 1 or in quadrant 4. So only in quadrant 4 the tangent is negative because it's positive up there. So we're going to be in the fourth quadrant, and this is minus square root of 3 over 3. So it's going to be minus pi over 6, because we know that tangent of pi over 6 is square root of 3 over 3. That's positive pi over 6. So, but this is first quadrant. We are in fourth quadrant, so it should be minus pi over 6. Let's do another example. So inverse tangent of tangent 2 pi over 3. Now 2 pi over 3, is that between negative pi over 2 and pi over 2? I don't think so, because that would be 2 times 180, that's 360. 360 divided by 3, that'll be 120 degrees. That's certainly not, this angle is not in the range negative pi over 2 and pi over 2. So let's calculate this. What is this value anyway? 2 pi over 3 is slightly less than pi, or 120 degrees, right? So if we are So if we are 2 pi over 3 would be somewhere here, in here. So that would be 90 plus 30 degrees. So 90 plus 30 degrees, or 120 degrees. And let's see, so that will give us, for the tangent function, that would be, so this would be tangent of, so 2 pi over 3, it should be square root of 3. Let me get some help from my calculator here. So 2 pi over 3, that would be 120 degrees, right? Or 360 degrees. So 2 times 180 is 360 divided by 3, 120 degrees. That angle is 120 degrees. So taking the tangent of that, we should get square root of, we should get something negative. So let's take the tangent of 120 degrees. So minus 1.73, which I bet should be square root of 3. So square root minus square root of 3, like that. Yes. So with 2 pi over 3, we are at 120 degrees, 90 plus 30 degrees. So this theta is going to be 30 degrees. So we can calculate the tangent as this side divided by the opposite side divided by the adjacent, one of the formulas we discussed in the first video. So this here is equal to tangent of 30 degrees, right? But, no, sorry, tangent of, right, so, okay, so let me bring this back again. So we're at 120 degrees here, which means the reference angle would be 60 degrees to complete this, right? If we're here at 120 degrees, then the reference angle would be 60 degrees, and that's where the tangent is negative. So the tangent of 60 degrees, square root of 3, right? Tangent of 60 degrees is, which is the reference angle for us, it's square root of 3. And because we're in the second quadrant, so this would be equal to inverse tangent of minus square root of 3. And of course, that's an angle we're looking for because it's inverse tangent of that. We're in the second quadrant, so it's minus pi over pi over tangent of what angle is, let's see, pi, so that's pi over 3, yes, so minus pi over 3 for that. So the point of this is that we can't go with this angle because it's outside of the range of negative pi over 2 to pi over 2. So we need to convert this to a reference angle that is between negative pi over 2 and pi over 2, and that's what we did here. Otherwise we would because we can't, if I can find that slide here, we cannot use the cancellation property outside of this range. See, you might be thinking, well, why don't we use the cancellation property, because this is inverse tangent of 2 pi over 3, so it would be equal to 2 pi over 3. No, we can't do that because the cancellation property can be used only for x values that are between negative pi over 2 and pi over 2. And we were outside of that range, so we couldn't use the cancellation property. So we had to do this. We had to find the reference angle instead and go from there. Okay, part E, tangent of so this is in here we're asking the sine of which angle. This is the inverse, right? This is not the inverse tangent. This is inverse. So in here, this whole thing is an angle. What angle is it? Any angle for which the sine is equal to 1 over 2. What angle is that? Well, let's bring back our special values. Right? The sine of 30 degrees is 1/2. So in here, we're going to say tangent of pi over 6, right? And then that is tangent of pi over 6 from our special values table. Tangent of pi over 6, right? It's equal to square root of 3 over 3. And note that this is between negative pi over 2 and pi over 2, right? So we can easily get the value from the special table of trigonometric values. So this is a square root of 3 over 3, like that. Okay, so let's move forward with the inverse secant function. Okay, we discussed this earlier for the secant function, right? This is page 4. We discussed this. So we decided that the domain is going to be restricted to 0 and pi over 2 and pi over 2 to pi, right? That's what we learned there. So let me quickly reproduce this on this page. Like that, and here is the y and the x, and the asymptotes are at pi over 2 and pi and that. So the asymptote was at right there. Remember, secant function is the reciprocal of the cosine function, right? And so I'm going to write that here. Secant of x is equal to 1 over cosine of x and so this was the so if we have a cosine function that does like this, let's bring it a little bit higher, like that. So that's the cosine function, and then secant function will be has a relationship with this, right? So like that. Okay, so this is cosine of x. The secant function will have to be between, and by the way, this is 1, and this is -1. So the secant function starts here, goes up, like that. So my arrow touched the dash, it shouldn't. So let me just draw it so like that. So that's one piece. The other piece is going to do like that. You can touch this, but not the vertical asymptote. So the other one was like that. And this point is pi. And this line, let me write that. So x equals pi over 2. So the blue dashed line is pi over 2, and this point is pi. Okay, so the secant function is restricted. Restricted over the interval x between 0 and pi over 2, and right, this and that, not this or that, but this and x between pi over 2 greater than pi over 2 less than or equal to pi. So we cannot touch the pi over 2 vertical axis. That's our vertical asymptote, and that's why you have strict inequalities here and here. Okay, so now limiting the so the domain is limited to this for the secant function. This is our domain, and let me do that. So this is domain of secant function. So what is the range? The range is 1 to positive infinity, negative infinity to 1, right? So let's write that down. And range of secant of x. This is important. Why? Because when we write down the domain and range for the inverse secant function, we're going to swap these, right? We're going to swap these to get the domain and range for the inverse secant function. That's why we care what these are. And so the range would be, let's write that down. So it would be 1, 2, I'm going to start from the smaller values. So I'm going to say negative infinity to negative 1 bracket union 1 to positive infinity. That's the restricted range for the restricted secant function. Okay, so how does the so the domain and range for the inverse secant function going to look like? So let's write that down. So for y equals secant, inverse secant function, we have simply reverse the role of the domain and range here. So we're going to say the domain is going to be the range for the secant function. So it's going to be negative infinity to negative 1 bracket union 1 to positive infinity parenthesis, and range of the, let me box this because like that. So the range is going to be the domain of the secant function. So I'm going to duplicate this domain for the range of the inverse secant function. Like that. So we have range is equal to x between 0 and pi over 2, and the other one, x between pi over 2 less than or equal to pi. I mean, we could write this using interval notation too. If you want, we can do that. We can say bracket 0 comma pi over 2 parenthesis union I should say or. So let me correct this to or. Well, this is and or actually. Union is and or, so it's fine. So and or the next one, which is parenthesis pi over 2 comma pi bracket. Okay, so that's that. So now let's draw the graph for the inverse secant function. We can easily do that using the information we have right in front of us, right? We know where the range is and where the domain is, so we can easily draw it. Let's do that. The range is all positive, so I'm going to give most of this blank space to the positive y-axis. So we're going to have the range 0, which is that. Let me move this up so you can see this. Okay, so this is 0, line 0, to pi over 2, so that's going to be an I shouldn't, when I talked about range, guys, I should say y. Sorry about that. So I should make this y and this y. And let's see, what else did I? So that the other ones should be on page 10 and 9. Let's see. So the range values. So I think the other ones, no, the other ones are okay. So the other ones are okay with that. Okay. So that's a correction I had to make. So that's range is y values, as you know. Okay. So I'm going to draw an asymptote for pi over 2, like that, and an asymptote for pi. We can't go beyond pi, right? Well, so let's see. So that one, well, within that range, actually, within that range, the only value we cannot, the only value of range that we cannot get is the pi over 2. So this one, I can actually make that a solid line. So this would be y equals pi. This would be y equals pi over 2, right? And then, so we have, so that's for the range. For the domain, it would be -1 to infinity. So it would be from a -1, let's say -1 is here or here, -1, and 1 would be here, -1 and 1. So that's -infinity to -1, so that would be and 1 to infinity. Okay, so this line, this piece of the inverse function moves in this direction, like that. That's for domain 1 to positive infinity. 1 to positive infinity. And this is secant. You know how the graph of secant works. The curves go in the opposite direction. So the inverse, for the inverse, it's the same way. So then we have at -1 to infinity. So this will be approaching the pi over 2 line from this side. So it'll be like this. Like that. Okay, so that's -1. That's that piece, negative infinity to -1. That's the domain. And the range, of course, is from 0 to pi over 2, which is the an asymptote, in this case a horizontal asymptote, which is the translation of this vertical asymptote now in horizontally. And this is from 1 to positive infinity, which is this piece. Okay, so this is the graph of y equals inverse of secant function. Okay, so let's do the inverse of cosecant function. Okay, cosecant function, as you recall, is connected to the sine function. Do you remember in which way? Well, if you answered the cosecant function is the reciprocal of the sine function, you're absolutely correct. So let me write that down, that the cosecant function, or the cosecant of x is equal to 1 over sine of x. So that's how they're related. Okay, so just like before, let me duplicate the graph we did for when we were finding out this one. So for the cosecant function, we determine how in which way the domain should be restricted. So I'm going to replicate this drawing here. And I'll do it quickly so we save time a little bit. Okay, so we know that x equals 0, or the y-axis, is a vertical asymptote, right? Because sine of 0 is going to be 0, and that would be dividing 1 by 0, which we can't have. So this y-axis is going to be our one of the vertical asymptotes for the cosine of x, cosecant function. So that is x equals 0. The next one is going to be x equals pi. Like that. Okay, so the sine function looks like this. And this side, oops, I went too far down. So let me do it like that. So like this and like that. Okay, and as you know, this is the peak here is 1, the low point is -1 here and here, roughly. Okay, so the cosecant function, we did, oh, by the way, so we decided to restricted domain is as follows. So restricted domain of y equals cosecant function was as follows. It is x greater than or equal to let's see, minus pi over 2 to 0, and x is greater than 0. This is from the page, from this page 4 that we did earlier. That's what I'm duplicating here. And greater than 0 and less than or equal to pi over 2. Okay, so that's what we did. So the range of this, oh, by the way, so I should draw the cosecant function, which would be here over the restricted domain, over this restricted domain. And I should draw the other side, which is negative pi. So negative so that should be x equals negative pi here. Okay, so for the cosecant function, the domain is limited to negative pi over 2 to 0, and pi over 2 has to be here. This is negative pi over 2 and to 0. So it's going to look like this. So this is going to start from here and do this. That's not the inverse of cosecant function. It's the restricted cosecant function according to this domain. That's what I'm drawing. And this piece is going to be from 0 to pi over 2. So that's negative pi over 2. This is pi over 2. So it's going to look like this, like that. So once again, this is the cosecant function over the restricted domain that you see here. Okay, so now we need to draw the cosecant function, inverse cosecant function. Let's do that. So the inverse cosecant function, and this is y equals that, this function. We have, so for this inverse cosecant function, we have, I want to word this like the previous page, so they flow more, they are more cohesive. Okay, so this, then the domain, we talked about domain next, so the domain of this should be the range of the cosecant function, and so the domain, I wrote it, the range, I didn't write that, the range of that is negative infinity to negative, oops, sorry. So let me correct this, guys. So I will correct it with my red ink. So the cosecant function touches the top and the bottom of the sine function. So I went too far. So let me correct that. So this line should curve like that. And please ignore that piece. So ignore that piece. This is the piece that is that. So it's going down to, it's coming from negative infinity to negative 1. So the range is negative infinity to negative 1 bracket union 1 to positive infinity. 1 to positive infinity parenthesis. Okay, so the domain of the inverse cosecant function is going to be equal to the range of the cosecant function. So we have domain is negative infinity to negative 1 bracket union 1 to infinity parenthesis, and the range is going to be the domain of the restricted cosecant function. So I'm going to duplicate that here. So the range is equal to, I'm going to use the interval notation. So 0 to comma pi over 2 union, so union, that would be so 0 to pi over 2 and negative pi over 2 to 0. Maybe I should have, so bracket negative pi over 2 comma 0, like that. So this should have been before that. Either way, so why don't I correct it? So mine bracket negative pi over 2 to 0 union 0 to pi over 2 bracket. So let me, I just swap the spots so it looks better. So this is the range. Okay, so now let's draw the graph for this, for the inverse of cosecant function. Okay, so we have the pi over 2 and the range is from negative pi over 2 to 0. So I'm going to draw that here. Right here would be good. So let me move this up a little bit. This is y equals minus pi over 2. I'm just looking at this range and plotting my line where the line should go. And 0 is the asymptote here. Y equals 0 is that one. So let me put a dashed line right next to it so it stands out as an horizontal asymptote. And actually, we can, according to this, touch the graph of the inverse cosecant function can touch this, the negative pi over 2 and y equals pi over 2. So let me draw these as a solid line. Like that. And this is y equals negative pi over 2 and also y equals pi over 2 right there. Just about like that. So this is y equals pi over 2. And the domain, of course, is negative infinity to negative 1. So I need to, on the x-axis, or along the x-axis, I need to mark off the negative 1 and 1. So negative 1, we can't be on this line. That's the horizontal asymptote. So I'm going to say negative 1 here, negative 1, and positive 1 here. Just about here. Okay, so then the range, so let's see. So this is going to be negative infinity to negative 1. So clearly, we're coming from here to this point. So that's one piece. The other piece should be on the other side. But if we're on the other side, where 1 is, right, 1, x equals 1, then then that's 1 to positive infinity. We can, this is our horizontal asymptote, but we can be on the pi over y equals pi over 2 line. So our line has to start from here and go this way, like that, and that is the 1 to infinity portion of this domain. Okay, so the range is from negative pi over 2 to pi over 2. We satisfied that with the y equals 0, and let me also write that. So y equals 0 here in the middle as the horizontal asymptote, and the domain negative 1 to, that's along the x-axis, right? Negative 1 to infinity, negative infinity to negative 1, and 1 on the other side to positive infinity. Okay, so let's draw the graph of the inverse cotangent function. That's the only one we haven't yet done. It would be the last inverse of a trigonometric function for today. So let's do that here. So this is the inverse cotangent function. So once again, I'm going to reproduce what we had here, what we discussed earlier, which was the cotangent function. This one, I'm going to reproduce the same exact drawing here. From page 4. And this is the graph of the cotangent of x function. Do you remember what connection cotangent function has with the other trigonometric functions? Think about it. Do you remember? Well, the cotangent is the reciprocal of the tangent function. So it will be cosine of x divided by sine of x, right? This is important. Why? Because wherever the sine of x is equal to 0, which would be at x equals 0, x equals pi, and so on, we're going to have a vertical asymptote. So let me draw the, so at x equals 0, we have this. That one. And x equals pi, we're going to have another vertical asymptote like that. And this middle here should be pi over 2, because cosine of pi over 2 is 0. 0 divided by anything is 0. So we're going to have the line going like this for the original cotangent function, right? Okay, so the domain of this cotangent function, in order for the cotangent function to have an inverse, was restricted, right? So the restricted domain, so let's say domain of y equals cotangent of x must be restricted to 0 to pi, right? So x must be between 0 and pi. Okay, so what about the range? The range here is negative infinity to infinity, right? There is no restriction there. It's the domain that has to be restricted. So the range of this cotangent function is negative infinity to infinity along the vertical or y-axis. Okay, this is important because when we write the domain and range for the inverse cotangent function, these two, the domain and range, are swapped. Okay, so let's write that down. So for the, let's see, so for, how did I write this? So for y equals inverse cotangent of x, for this, we have the domain is going to be the range of the original cotangent function. So the domain is going to be negative infinity to infinity, right? And the range, let me move this up. And the range, well, I'm going to bring it down. So the range is going to be the domain of the original cotangent function. So the range is going to be from y equals y from 0 to pi, or using the interval notation, it's going to be parentheses 0 comma pi parenthesis. Okay. Now with these two pieces of information, we can draw the graph for the inverse cotangent function. Let's do that. So this is y equals inverse cotangent of x. All right, so looking at this, the range is going to go from 0 to pi, not including 0 and pi, right? Because we have parentheses. And 0, y equals 0, which is the x-axis, is going to be our one of the horizontal asymptotes, and y equals pi is going to be the other horizontal asymptote. And we cannot touch those with our graph. So let's draw that. This is y equals pi, and here, this is, let me put a dashed line right on top of my x-axis because it is a horizontal asymptote, like that. And this is y equals 0. And so that's the range. We're going to be bound by these two horizontal asymptotes. And the domain is going to be negative infinity to infinity. So apparently our line is going to go like this. So we're going to come from negative infinity. So it's going to be, this is going to be the pi over 2, right? So this is pi over 2. Halfway between y equals 0 and pi. And so our graph is going to be like that. And like that. So if I find my tangent, or inverse tangent, it's somewhere here among these. We can compare them side by side. And so let's see, that's cosecant, and that's, so I'm looking for my inverse tangent. You're going to have it posted I'm going to post this, but while we're at it, why not look at it one more time, just to compare the inverse of secant or inverse of tangent and inverse of cotangent functions side by side. Oh, it's right there. So notice this is the graph of the inverse cotangent function. It's going like that, right? And the inverse of the tangent function is going like that. So the opposite of each other, right? Okay, so I just wanted to make a comparison before we close this section. This wraps up our discussion of inverse of basic trigonometric functions. And so please post your solutions on the discussion board right underneath the video, and or come to my office hours. And once again, I'm very glad that you persisted through this video. And if you have to, please rewind and take a look at what we've talked about, what I've talked about in this video, and stop by with your questions. Again, thank you for persisting through the video, and have a very nice day, and I'll see you all next time.